America may not have lost the Western Pacific yet, but the military advantage it spent decades and trillions of dollars building is now disappearing faster than Washington expected. For more than 20 years, the United States believed technological superiority would guarantee military superiority. But what happens when a rival can access parts of that innovation without paying the full price of discovery? Has China truly overtaken the United States Navy? How has Beijing exploited American defense technology, industrial knowledge, and artificial intelligence? And when headlines claim China ripped off a $1 trillion American AI war plan, are they describing a documented theft, combining decades of investment into one dramatic figure, or simply exaggerating a far more complicated threat? The first shock comes from the fleet count. By the most commonly cited measure, China now possesses a larger naval battle force than the United States when warships are counted by hull numbers. But hulls do not fight wars by themselves. America still commands far greater fleet tonnage, nuclear-powered aircraft carriers, advanced nuclear submarines, global expeditionary experience, overseas bases, and an alliance network China cannot easily replicate. A single American carrier strike group can project more sustained combat power than several smaller surface formations. Yet the Western Pacific is not an open scoreboard. China would be fighting close to its own shipyards, airfields, sensors, logistics networks, and command infrastructure. It can concentrate forces near its coastline while surrounding approaching American units with dense layers of land-based missiles, aircraft, submarines, drones, and surveillance systems. The United States may remain stronger globally while facing an increasingly dangerous local balance. This is not a simple story of China copying American weapons and instantly becoming superior. It is a competition between two different strategic models. The American model invests heavily in foundational science, breakthrough technologies, exquisite platforms, and military operations across the globe. The Chinese model combines domestic research with technology transfer, intelligence collection, commercial acquisition, massive manufacturing capacity, and rapid, repeated improvement. That distinction matters. When we say America has been ripped, we do not mean China stole the entire American defense system or obtained a single master file containing every future war plan. We mean that American data, intellectual property, research, and technological advantages have been systematically targeted, absorbed, and converted into usable capability. The greatest danger is not one stolen blueprint. It is China's growing ability to shorten the cycle between acquiring knowledge, adapting it, testing it, and manufacturing the result at scale. In modern warfare, speed of iteration may matter almost as much as the original invention. That is the real contest ahead. Naval power, copied technology, AI distillation, autonomous swarms, industrial scale, defense investment, and Washington's attempt to respond before its remaining advantages become too expensive, too slow, or too fragile to matter. To understand how much ground America has actually lost, we must begin with what those fleet numbers truly reveal. Fleet numbers are not a simple scoreboard. The phrase battle force ships is a statistical category designed to measure vessels considered part of a nation's operational fleet. It does not mean every hull carries the same combat value. A small missile craft, patrol vessel, or lightly armed escort cannot be placed on the same scale as a nuclear-powered aircraft carrier, an attack submarine, or a guided missile destroyer. The numbers also shift depending on the year, the classification method, ships undergoing maintenance, and vessels technically commissioned, but not truly ready for deployment. So when reports cite more than 370 Chinese ships, the figure must be treated as a measurement, not a verdict. By the most important measures, America still holds formidable advantages. The United States Navy possesses far greater total tonnage and can carry more weapons, fuel, sensors, and aircraft across the ocean. Its nuclear carrier fleet remains unmatched in scale, supported by air wings with decades of combat experience and global operations behind them. American nuclear-powered attack submarines can travel farther, remain at sea longer, and hunt across vast distances without depending on vulnerable resupply points. Behind them stands an enormous architecture of tankers, transports, repair ships, bases, communications networks, and logistics commands capable of sustaining military power across continents. Washington also operates through a network of partners: Japan, South Korea, Australia, the Philippines, and other regional allies. Its intelligence, surveillance, reconnaissance, and joint command systems have been refined through generations of exercises, deployments, and war planning. But China's advantage is not measured by what it can do everywhere. It is measured by what it can concentrate near home. The People's Liberation Army Navy operates close to a dense supporting system of land-based anti-ship missiles, aircraft, satellites, radar networks, and Coast Guard forces. Its supply lines are shorter. Its aircraft can return to nearby bases. Its ships can operate under the protection of a wider military sensor and missile architecture. And behind that fleet stands an industrial machine of extraordinary scale, combining commercial shipbuilding capacity with rapidly expanding military production. China can replace losses, launch new hulls, and expand its force at a tempo that creates a problem no single American carrier group can solve. In a crisis around Taiwan, Beijing does not need to dominate every ocean. It only needs local superiority at the decisive place for the decisive window. On the map, that window stretches across the Taiwan Strait, the East China Sea, the South China Sea, Okinawa, and Guam. China's strategy is to push American forces outward, forcing them to fight from greater distances while exposing tankers, bases, communications, and supply routes to attack. A precise missile strike or a coordinated cyber attack against logistics could reduce the effectiveness of platforms costing billions of dollars. China has not replaced America as a global naval power, but it has built enough strength to challenge the United States in the region that matters most to Beijing. And ship counts are only the surface. The more controversial question is where China obtained the technology used to build this force. That question leads to one of the most persistent arguments in modern defense analysis. From the F-35 to the J-20, is China copying, stealing, or developing independently? The answer is more complicated than any single label. The term Shanzhai usually describes an imitation, often a cheaper replica or a modified version of an existing product. It can be useful when discussing consumer goods, but it is too blunt to describe China's entire defense industry. China was not historically a civilization without invention. It produced major military innovations, including gunpowder, rockets, and advanced naval technologies. Today, it also possesses one of the world's largest research systems, supported by state funding, universities, military laboratories, and industrial conglomerates. To claim that Beijing invents nothing is not just inaccurate. It makes the analysis less credible. China has used multiple paths to accelerate technological development. Western governments and companies have documented cyber intrusions targeting state agencies, defense contractors, subcontractors, and universities. Intelligence operations have sought technical information and recruited specialists. Companies have been acquired, partnerships established, and technology transferred through joint ventures, licensing arrangements, and industrial cooperation. Other channels are less dramatic, but equally important. Public research papers, patents, scientific conferences, commercial software, legally purchased equipment, and systems obtained through third countries. Chinese engineers trained abroad have also returned with knowledge that could be absorbed into domestic research networks. The F-35 illustrates the difficulty of separating evidence from assumption. Western officials and investigations have accused China-linked actors of stealing sensitive data connected to the program. There is evidence of cyber campaigns. There are serious allegations that defense information was removed. But that does not prove every feature of the J-20 or the FC-31 is a direct copy of the F-35. External resemblance is not technical proof. The real questions involve sensor performance, engine reliability, radar absorbent materials, electronic warfare, software, and mission systems. A similar silhouette does not reveal how an aircraft sees, communicates, survives, or fights. And a design file is not an operational capability. A modern fighter requires specialized materials, precision machine tools, secure supply chains, propulsion technology, software, testing procedures, and thousands of engineers who understand how every component behaves under stress. Stolen data may save years of research, expose weaknesses, or prevent expensive dead ends. But it cannot automatically create a production ecosystem. China has still had to invest for decades in jet engines, phased array radar, avionics, pilot training, and manufacturing quality. The strategic value of stolen information is not magic. It is reduced uncertainty. It helps direct money, talent, and political attention toward the most promising path. China's broader model can be understood as 4 steps: access, absorption, adaptation, and production. Access knowledge from inside and outside the country. Absorb it through research institutes and corporations. Adapt it to Chinese doctrine and military priorities. Then produce it at scale, potentially lowering the cost of each additional system. That is the deeper advantage, not copying alone, but an ecosystem capable of turning information into deployable power. And if aircraft designs were once the most valuable technical assets, the age of artificial intelligence is about to change the definition of what must be protected. Because now, the prize may not be the model itself, but the outputs it generates. Those outputs can become a new form of training material. This is where model distillation enters the battlefield. Imagine a powerful AI as a teacher. It receives thousands, perhaps millions, of carefully designed questions, then produces answers, explanations, code, classifications, or strategic assessments. A smaller student model studies those responses and learns to reproduce part of the teacher's behavior. The result may be less capable but cheaper, faster to develop, and compact enough to operate on restricted hardware. Distillation is common across the AI industry. By itself, it is not proof of theft. The decisive question is how the outputs were obtained and what the license permits. If a developer uses an API within its authorized terms, generating training data may be lawful. But automated extraction at massive scale, designed to replicate a protected service, may violate contractual restrictions. Fake accounts, unauthorized access, evasion of export controls, or deliberate circumvention of security barriers belong to a more serious category. And crucial distinctions matter. Stealing model weights is not the same as learning from outputs. Taking source code is not the same as observing responses. Exfiltrating private training data is not the same as querying a publicly accessible system. Calling every case AI theft may sound dramatic, but without evidence, it obscures more than it reveals. The military implications, however, are real. A distilled model could help analyze satellite imagery and reconnaissance feeds, flag potential targets while leaving decisions about force under human control, optimize logistics, predict maintenance failures, allocate ammunition, simulate battlefield conditions, support command staffs, detect cyber anomalies, examine malware, or coordinate unmanned vehicles when communications are degraded or jammed. Commercial models matter because their underlying capabilities are broad. They can process language, imagery, software code, and multimodal sensor data. A civilian foundation model does not instantly become a weapon, but it can provide a powerful base layer for specialized fine-tuning, shortening the journey from general intelligence to operational capability. The expense being avoided is not measured only in graphics processors. It includes curated data, electricity, scarce expertise, repeated experiments, failed designs, and months of uncertainty. Access to the outputs of a stronger model can reduce that trial and error, allowing a competitor to search the technological landscape more efficiently. Yet distillation is not duplication. A student rarely inherits the teacher's full capability. It may also absorb errors, bias, fabricated information, and hidden weaknesses. In combat, those weaknesses become dangerous. Military systems must function amid corrupted data, interrupted networks, electronic interference, and an enemy actively constructing deception. Without public evidence, no one should claim that a specific American model directly trained a specific Chinese weapon system. Possibility is not proof, and inference is not attribution. Because AI creates a decisive advantage only when connected to sensors, communication networks, command structures, and combat platforms. So first, define the machines. A swarm of unmanned aircraft is not the same as a formation of manned fighters. Loitering munitions are not reusable combat jets. And 100 entities inside a computer simulation are not 100 aircraft surviving enemy fire. Coordinating 100 vehicles does not mean a single artificial intelligence is directly flying 100 advanced fighters in real combat. A laboratory demonstration may prove an algorithm. It does not prove an operational weapon. And any claim tied to the 4th of August 2026, if that date has not occurred or lacks independent verification, must remain an unverified claim, not an established event. A genuine swarm would operate through distributed intent. A commander assigns the objective, the boundaries, and the rules. The software then divides responsibilities. Some vehicles search. Some jam radar. Some create false signatures. Others relay communications, map defenses, or approach designated targets. They exchange data, reposition, and reorganize as conditions change. If communications collapse, each unit needs fallback instructions governing navigation, formation, retreat, and survival. Human operators may still retain final authority over target approval and weapons release. Autonomy is therefore not necessarily the removal of humans. It is the compression of decision time. Its military value is brutal. A defending radar can track only so many objects. A missile battery carries only so many interceptors. Send inexpensive decoys beside reconnaissance drones and strike platforms, and the defender must decide what is real, what is dangerous, and what deserves a missile costing vastly more than its target. The swarm expands sensor coverage, attacks from multiple directions, and accepts losses without losing pilots. Combined with high-end aircraft, expendable mass can impose an unforgiving economic equation. The attacker risks cheap machines, while the defender burns scarce weapons merely to remain alive. But scale magnifies weakness as quickly as strength. Data links can be jammed, intercepted, or spoofed. GPS signals can be manipulated. Sensors can misclassify civilian objects, TOV'd, or friendly forces. An AI trained on familiar patterns may respond unpredictably when confronted by a tactic it has never encountered. Hundreds of coordinated vehicles demand bandwidth, precise timing, constant testing, secure updates, and resilient software. One defect copied across the entire formation does not create one malfunction. It can create systemic collapse. For the United States, the warning is clear. Superior performance concentrated in a small number of exquisite platforms is no longer sufficient. America also needs distributed, affordable, replaceable systems that can fight without relying on one command center. It needs counter-drone weapons whose interception cost does not bankrupt the defender. And it must train under the conditions an advanced enemy would impose: satellites degraded, GPS denied, networks fractured, and communications reduced to moments. Because this race will not be decided by one algorithm. It will be decided by which nation can produce hardware, chips, ships, missiles, and software at scale. There is no single vault labeled AI warfare plan holding $1 trillion receipt. That number is usually a constructed estimate, assembled from years of defense budgets, semiconductor incentives, data center construction, artificial intelligence research, weapons programs, and the opportunity cost of redirecting industrial capacity toward military competition. Without a verified budget document, it cannot be presented as audited damage. The responsible headline is not $1 trillion lost. It is a question: how much could this competition ultimately cost? The American investment is already spread across multiple layers. The CHIPS and Science Act allocated approximately $52.7 billion for semiconductor manufacturing, research, and workforce development. The Pentagon and other federal agencies invest separately in computing, autonomy, military data, tactical networks, and basic research. Meanwhile, private companies are spending tens of billions on models, advanced processors, cloud systems, and data centers. Together, that ecosystem may be enormous. But it is not the same as the cost of building one military AI model. It is the price of constructing the industrial foundation beneath an entire technological era. China enters this contest with a powerful advantage: the ability to learn from architectures, standards, and commercial products that have already been tested elsewhere. A later mover can concentrate capital, land, energy, state-backed financing, and procurement around selected priorities. Its enormous domestic market can provide data, engineers, and scale for experimentation. Civil-military integration can allow commercial technologies to be evaluated rapidly for defense applications, compressing the distance between a product demonstration and a military requirement. But this advantage has limits. China still faces restrictions in advanced chips, semiconductor manufacturing equipment, industrial software, and specialized components. Scale can accelerate production. It cannot instantly erase bottlenecks at the frontier. America's vulnerability is different. It possesses exceptional laboratories, companies, and military systems, yet its procurement cycles remain painfully slow. Dependence on a limited number of major contractors creates concentrated supply chains. Shipbuilding capacity, ammunition production, and maintenance networks cannot be expanded overnight. A technology that works in a laboratory may require years to reach an operational unit. Security classifications can restrict data. Fragmented systems can prevent algorithms from communicating across platforms. And an innovation advantage that cannot survive procurement is not an advantage for long. This is why protecting secrets is not enough. Washington must also accelerate the conversion of technology into deployable capability before competitors turn industrial patience into strategic momentum. The correct measure is not the price of a platform alone. It is the cost of producing each military effect. How fast can a prototype become a weapon? How quickly can losses be replaced? Can supply chains survive a crisis? Can software be updated without weakening safety? The nation that answers those questions will define the battlefield of the next decade. So, can Washington prevent technological exploitation without isolating the AI industry that gives it an advantage? Washington's response begins with the first line of defense, controlling the hardware that makes advanced AI possible. That means restricting exports of high-end GPUs, semiconductor manufacturing equipment, and the technical services that keep them operational. It also means tracking shipments routed through third countries, shell companies, and intermediaries designed to disguise the final destination. Increasingly, attention is turning toward cloud computing itself, because a restricted entity may not need to physically possess an advanced processor if it can rent the training capacity from somewhere else. But export controls are not a perfect wall. They raise costs, slow development, complicate logistics, and reduce access to the most capable systems. They do not guarantee an absolute blockade. Determined actors can search for substitutes, exploit loopholes, acquire older hardware in large quantities, or build domestic alternatives over time. The second line of defense protects what the hardware alone cannot reveal: models, data, code, and deployment systems. Companies will need stronger customer verification, continuous monitoring for abnormal queries, and limits on behavior designed to collect massive volumes of model outputs. Model weights, source code, fine-tuning data, and operational infrastructure must be treated as strategic assets. Commercial AI environments must remain separated from sensitive military data, while even small defense contractors must meet cybersecurity standards appropriate to their position in the supply chain. That does not mean presenting a proposed ban on Chinese data centers as an existing policy. Drafts, recommendations, and enacted rules are not the same thing. In this contest, precision matters because exaggerated claims can weaken the credibility of legitimate security measures. The third line of defense is more difficult because it requires Washington to repair its own defense system. Software testing and procurement must move faster. Long-term contracts must give industry the confidence to expand production of ammunition, components, and replacement systems. Open architectures can allow sensors, algorithms, and hardware to be exchanged without rebuilding an entire platform. Low-cost drones, electronic warfare, base defense, ship repair, spare parts reserves, and dispersed forces across the region are no longer optional improvements. They are the foundation of resilience. And America cannot do this alone. Japan and South Korea bring shipbuilding, electronics, and industrial capacity. Australia offers strategic depth, training space, and logistical potential. The Philippines provides critical access near the first island chain. Taiwan needs survivable forces, hardened stockpiles, and asymmetric systems designed to keep fighting under pressure. Technology controls work only when allies share standards, intelligence, and enforcement mechanisms. So what is the final verdict? China has a documented history of cyber espionage and, in many cases, has been identified conducting operations against American technology. But China also possesses genuine research, manufacturing, and innovation capabilities. Its military rise cannot be explained entirely by copying. AI distillation may narrow the gap. It does not mean obtaining an entire model or an entire battle plan. And the figure of $1 trillion should not be presented as proven stolen value without specific budget records and technical evidence. America has not lost its entire military advantage. But the era of near technological monopoly in the Western Pacific is over. China does not need to copy perfectly. It only needs to learn fast enough, produce in sufficient volume, and deploy close enough to the battlefield. The decisive contest is not who invents first, but who protects knowledge, converts it into capability faster, and sustains that capability when war fractures every supply chain. Follow this channel for more evidence-based analysis of the military balance shaping the next decade.